In this discussion, we're going to talk about tests for determining additional tests for determining whether series converge or diverge. Not what they converge to, but simply whether they converge or diverge. And this pair of tests are called series comparison tests. And there's two different ones, the direct comparison test and the limit comparison test. And so we're going to start first with the direct comparison test, and then we'll move to the limit comparison test. Well, the direct comparison test says this. In fact, let me put this up so that we can concentrate on the pieces that we need to at a time rather than being overwhelmed by everything. So let's assume that we have two series, okay, made up of A sub n's and B sub n's. That is the terms of the series, A sub n's and B sub n's. And every term of one series is smaller than or equal to every corresponding term of the second series. Okay, so term by term, the first series is smaller than the second series. And all of the terms are non-negative, either positive or zero, but never negative. Well, here's the direct compare. There's two parts to the direct comparison test, and what we're doing is we're directly comparing the convergence or divergence of the two series. So if the second series converges, then the first series also converges. And that's probably not what I should say. I shouldn't say the second series and the first series. But what this is the series of all the larger terms. So what I could say is if the larger series, see, this is the larger series because all these terms are bigger. If the larger series converges, then the smaller series must also converge. And after all, if we add up all these B sub n's and they add to a finite number, but all the A sub n's are smaller than all the B sub n's, then adding up all of the A sub n's should also add up to a finite number. So that's the idea. If the larger series converges, then the smaller series can't add to more, so it also has to converge. Now, this says if the sum of the A sub n's diverges, then the sum of the B sub n's also has to diverge. After all of these A sub n's are smaller than all of these B sub n's. So if we add up an infinite number of these A sub n's and it adds to infinity, then if we add up a bunch of bigger numbers, that also has to add up to infinity. So another way to say this is if the smaller series diverges, there's no way for the larger series to converge because it has to be bigger. So the larger series also has to diverge. If the smaller series diverges, then the larger series diverges. If the larger series converges, then the smaller series converges. What is not said, I don't think I wrote this down. What is not said is if the smaller series converges, that tells us nothing about the larger series. Or if the larger series converges, then that tells us nothing about the smaller series, diverges. So be careful, okay? Be careful. And let me repeat that. This does not say if the smaller series converges, we know the larger series converges. In other words, it doesn't tell us that if the sum of A sub n's converges, that we can determine that the sum of B sub n's converge. They may be much bigger. Or it doesn't tell us that if the sum of the B sub n's diverge, then the sum of the A sub n's also. It doesn't say that. If the sum of the B sub n's diverge, then the sum of the A sub n's might diverge, they might converge. They're all smaller, so we don't know. Okay? So we need to keep that in mind. If one of those other scenarios plays out, that is, if we have the sum of the A sub n's converges, then we know nothing. If we have the sum of the B sub n's diverges, then we know nothing. It's only if we know the sum of the larger converges or the sum of the smaller diverges. That's when we can make a conclusion. Be careful, please. It's an important point. Well, let's see how we would use this. Our first problem. Determine the convergence or divergence, if we can. We may not be able to tell. For the series from n equal 1 to infinity of 1 over n plus 3 to the nth power. Now, here's the tough part, and this is a tough part. I'm going to, and we really don't know whether this is going to be the a sub n's or this is going to be the b sub n's. This is a tough part. I don't have another way to say it. But what I've chosen is this 1 over n plus 3 to the nth power to be my a sub n's. And the reason I've chosen that is because I can compare this. I'm looking for something to compare this term to. And about all I could do is lop away the n or lop away the 3 to the n. If I lop away the n, okay, if I lop away the n and compare it to 1 over 3 to the n, this denominator is smaller because I don't have a plus n in there, right? It's smaller, okay? And if it's smaller, the denominator is smaller, then the fraction is bigger. That is, as long as the numerator isn't changing. So the numerator is constant, and the denominator is smaller, so the fraction is bigger. So now that's the reason I want this to be a sub n's, because these are all smaller than these. So these are my a sub n's, these are my b sub n's. Well, what good is that? Well, here's what good it is. The series that I started with, this series, is less than or equal to this series, okay? Because these terms are less than or equal to these terms. But this is a geometric series. This is a geometric series where r is 1/3. Okay, and we've seen these ideas. R is 1/3 here. And if r is 1/3, then this series converges. So the larger series converges. How could the smaller series diverge? It couldn't, could it? So the larger series that we have here converges, and that tells us then the smaller series must also converge based on the direct comparison test. So coming up with a comparison can be quite tricky, as you see here. Let's look at the next problem. Now here we're to determine the convergence or divergence of the sum from n equal 1 to infinity of 1 over 2 plus the square root of n. Now, I've got to come up with an a sub n series and a b sub n series. I've got to come up with those. And then I've got to be able to compare and decide either the sum of the a sub n's converges or something about the convergence or divergence of the sum of the a sub n's. Okay. Now the issue is, if I make these a sub n's, I've got to come up with a series that's larger to do any good, that's larger, okay, that converges. Or if I make these the b sub n's, I'm going to come up with a series of a sub n's, okay, where the series of a sub n's diverges. Okay, so I can compare to this. Let's go about our problem. Here I'm deciding to make these, this is a test case basically. Okay, and so here's how I'm testing it. If I don't know any better, I'm going to call these terms the a sub n terms. So now I've got to come up with some b sub n's to compare with. Well, about the only thing I could think of is lopping off the 2 here, okay? And so if I compare 1 over 2 plus the square root of n, and I make the denominator smaller, now remember the numerator is not changing. So if the denominator is smaller, the fraction is bigger. And so I have a way to compare this to this, that is a sub n's are smaller than b sub n's. Okay. Now, here's what we know. The smaller series, of course, is less than or equal to the larger series. And the larger series, made up of the sum of 1 over square root of n's, diverges, because this is a p series, isn't it? Where p is the exponent 1/2. And since that's smaller than 1, we know this series diverges. So we say we have a smaller series than one that diverges. That tells us nothing about, okay, that is, the larger series diverges, but that tells us nothing about the smaller series. The smaller series could diverge, but the smaller series could also converge. All we know is it's smaller than the one that diverges, so that doesn't really tell us anything. And so this comparison didn't do very much, did it? And there's not a whole lot else I could easily do. I mean, I can't make very easily this something that's larger that I would know how to deal with. Okay, so the series, the test in this case is inconclusive. It's not something that we can always use, and sometimes it's difficult to use at all. Okay, so be careful. Just because we know the larger series diverges, that tells us nothing about the smaller series. Or if we know the smaller series converges, that tells us nothing about the larger series. I think I've warned you enough about that, haven't I? Let's move on. Let's determine here, we're asked to determine the convergence or divergence of the series of n over n cubed plus 4. Now, again, we're using the direct comparison test. So we've got to come up with another series that we know something about. Okay, if we come up with a smaller series, we only want it to diverge, because then we would have the larger series, which is this one, diverging also. Or if we come up with a larger series, we want the larger series to converge, because this one would be smaller, and that would tell us it would converge. Anything else is useless. So the big job always is to determine what is a sub n and what is b sub n. This is not always the a sub n's, but that's what I'm choosing to try, okay, because it's just what I'm deciding to try. And I'm using the same idea, is that I can make this denominator smaller, and if I make the denominator smaller, the fraction becomes bigger, as long as I don't change the numerator. So that's what I've done. I've not changed the numerator, but I've made the denominator smaller, so this fraction's bigger. And of course, this fraction will simplify to 1 over n squared. And so and what good is that? Well, if I look at the series of 1 over n squareds, we know that that is a p series. And it's a p series where p is 2, which is bigger than 1, so it converges. So I've got a smaller series, okay? My original series is smaller than a series that I know converges. So if the larger series converges, certainly the smaller series has to converge also. And so we've used this test, the direct comparison test, to determine that our original series converges, because it's smaller than another series that we do know converges. So that's the way we would go about this again. Well, let's continue. Okay, here we want to know whether the sum of the natural log of n plus 2 over n converges or diverges. And we're going to try the direct comparison test. Let's see what we can do. And once again, there's a big question on how we choose a sub n and how we choose b sub n. Every time we've chosen, so far we've chosen a sub n to be the terms of the given series, but that may not always be the case. Now, here's what I'm looking at over here. I'm looking at the natural log of n plus 2. And I'm just thinking about what that graph looks like. And so it's, of course, shifted to the left 2 units. And so then if I let n be equal to 1, that would be right here, wouldn't it? Then the natural log of 1 plus 2, or the natural log of 3, is a 1.099. Okay, so it's a little above 1 right here. Now, why am I interested in that? Well, here's why I'm interested in that. Because Now I know that the natural log of n plus 2 is bigger than 1 for all n's that are greater than or equal to 1. And that allows me to make a comparison. Okay, so here's, in this case, look what I've done. The natural log of n plus 2 is bigger than 1. So if I divide both sides by a number that is bigger than 1, that's positive, then I have this fraction has to be bigger than this fraction. So that took some clever thinking, didn't it? Ingenious thinking. Now, I'm not claiming that I'm clever, but in this case, I am. I struggled behind the scenes a lot before I did this problem. Okay, I struggled. Maybe you don't believe that, but I'm trying to give the story. I struggled with coming up with a comparison, and that's one thing we can do sometimes, is compare a numerator with another proposed numerator, and then we can compare the fractions if the denominators are the same. So a little twist to that, wasn't there? So I just rewrote this differently. So I had the smaller term on the left, so I could write it in a fashion that we're used to. Now that means the sum of the 1 sub n's is smaller than the sum of the natural log of n plus 2 over n. In other words, this time the 1 over n's are the a sub n's, and this fraction are the b sub n's. So we have a series of 1 over n's that's smaller than a series that's smaller than our series. Now, the series of the 1 over n's diverges. This is a harmonic series. It's a p series where p is equal to 1, and when that's the case, then we know that that series diverges. So this series diverges, which is smaller than this series. So this series can't add up to something smaller. It has to also diverge, and that's our conclusion then. The smaller series diverges, therefore the larger series must also diverge, and the larger series is the series in question. Well, sometimes it's an easy test to use, and other times it's very difficult. So I'd like to switch gears at this point and talk about the other comparison test, series comparison test, called the limit comparison test. Now, what we've been looking at is the direct comparison test, where we're comparing the convergence and divergence of two series to make a decision. Okay, so here's what the direct comparison test says. Suppose we have a series made up of a sub n's that are all positive, none are zero, and a series of b sub n's that are all positive, none are zero. And if we look at the limit of the corresponding terms of the two series, that is the a sub n's divided by the b sub n's as n goes to infinity, and that limit is equal to L, where L is a number that is finite. That means it's not infinite, of course. It's not infinity. And that limit is positive, not zero, a positive number. In other words, the limit is a positive number. It's not zero and it's not infinity. Then the series of a sub n's and the series of b sub n's either both converge or both diverge. We can't have one of each. Now, that's pretty significant, okay? And this is actually a little easier test to use than the one we just looked at. But let me try to convince you of why this is the case. The limit of a sub n over b sub n would be the limit of a sub n over the limit of b sub n, and we know that that is a finite positive number. Now, let's see if I can say this correctly. If we were to have the top series converge and the bottom series diverge, then the limit of the a sub n's would have to go to 0, and the limit of the b sub n's would not go to 0. And so that would mean the limit would actually be equal to 0. See, for a series to converge, okay, for a series to converge, so if the top series converges and the bottom series diverges, Well, for a series to converge, that the limit would have to, of the a sub n's would actually have to go to 0. That means the limit up here would be 0. And so we couldn't have 0 over a number is equal to a non-zero number. So that tells us that we can't have this go to 0 and this not go to 0. Now, 0 over 0 is indeterminate, and that might not be 0, but we can have a 0 result here and a non-zero result here. So that tells us that we know that we can't have one converge and the other diverge. Now, likewise, on the other case, if we had the series here diverge and the series here converge, well, that would mean if this series converges, the limit of the b sub n's is 0. Now, we couldn't have the limit of the a sub n's also 0, because then we would have an indeterminate form. And that indeterminate form, we don't know much about. But if we have a divergent series here, okay, if we have a divergent series here, let's look at it that way, and convergence, most likely these are not going to, the limit's not going to go to 0. The limit here has got to go to 0, and so the limit would have to be infinity, not L. And I mean, that's just a rough talk. We don't really need to be concerned. I'm trying to convince you that it makes sense of what this limit comparison test says without a formal proof. And certainly I haven't given it a formal proof. Okay, well, let's see about using it. Whoops, I gave you a glimpse of the whole next slide accidentally, so let's start that over again. Now this is using the limit comparison test. And here's our first problem, is to determine the convergence or divergence of the series from n equal 2 to infinity of n, of n over n cubed minus 2. The reason this is starting at n equal 2, I've got this note over on the right, is if n is equal to 1, we would have 1 over 1 minus 2, which would be negative. So remember, the limit comparison test requires that all of the terms be greater than 0. They can't be 0 and they can't be negative. And so that's the reason that we're concerned about having n greater than or equal to 2 here. Now, obviously, if we can determine that this series converges, then n equal 1 to infinity would also converge, because we're just adding one more term. Or if we determine this series diverge, then n equal 1 to infinity would also diverge, because we're adding an additional term. Well, here's what we're going to do, okay? And I'm going to give you a quick way to make these decisions after this problem, okay? So I'm going to take the series that we've got, and I'm going to compare it with a series of n over n cubed from n equal 2 to infinity. But n over n cubed, of course, simplifies to 1 over n squared, okay? Now, what I'm going to do is I'm comparing this series with one that is a p-series. And it's a p-series where p is 2, which is greater than 1, so it converges. So we know these two series, we know this series converges. So the test then, the test is to look at the limit of the a sub n's divided by the b sub n's. That's the test. Okay, we're not comparing the series, we're looking at a limit. Now the a sub n's are n over n cubed minus 2. And the b sub n's are 1 over n squared. And so I'm looking at this limit. Now all I'm doing here is algebraically simplifying this. I'm multiplying by the reciprocal of 1 over n squared, which gives me, of course, n cubed over n cubed minus 2. So we're looking at the limit as n approaches infinity of this fraction. Now, this is the type of problem that we've dealt with in Calculus 1. I'm noticing the biggest power of n in the denominator is 3, and so I'm going to multiply the denominator by 1 over n cubed, and likewise the numerator by 1 over n cubed. And when I do, I get 1 in the numerator, and I get 1 minus 2 over n cubed in the denominator. And so when I'm looking at the limit of this adjusted fraction, I get 1 over 1 minus 0, or 1. Now, that significance is that this limit is a positive finite number. And if the limit of the ratio of the terms is a positive finite number, and all of the terms are positive in both series, then we can draw a conclusion. And that conclusion is, well, here's what I said. The limit of the ratio is 1, which is greater than 0, and it's finite. And we already know that the sum, the series of b sub n's, converges because that's a p-series. Then by the limit comparison test, our other series, the one we want to know about, must also converge. So we didn't compare the series directly, we compared a limit of the ratio of the terms. And you might say, well, why didn't we just compare the two series directly? And here's the reason that come into view. The direct comparison test would not have worked well here, because in this case, about all I could do is replace that denominator with just n cubed. And what has happened there? In this case, I'm subtracting 2. So this denominator is smaller than the denominator here. So that makes, and the numerator hasn't changed. So if we have a smaller denominator, then we have a bigger fraction. So this series adds up to greater than this series. And this series, of course, is a series that converges. Well, just because this adds up to a finite number, if this adds up to something greater, it might be infinity. And so we can draw no conclusion. And that's what we said previously with the direct comparison test. If the smaller series converges, which is what we've got here, that gives no conclusion about whether the larger series converges or diverges. And so the direct comparison test would not have worked in this case. And it's because of the type of terms we had. Well, remember, I made a decision to compare to a series of b sub n's that I just locked down and didn't explain why. And in the next step, in the next slide, I'm going to explain why. As you can read here, this is about when and how to use the limit comparison test. Now, this doesn't say that this is the only time you would use it, but there is a very good time to use it. And as you can read, the limit comparison test works very well for comparing a messy algebraic series with an appropriate p-series. And to choose the p-series, what we do is to choose the one we're going to compare to, we disregard, in the original series, we disregard all but the highest power of n in both the numerator and denominator. Let's back up. Here is my series. I look at the numerator. There's only one part of the numerator, okay, and it's n, and so that's the highest power of n in the numerator. So I use that numerator. I look at the denominator. I've got two terms. One is an n cubed, the other is a minus 2. This doesn't involve n, and so I disregard it. That's the reason I have an n cubed here. And then my resulting fraction simplifies to a p-series, which in this case converged. That's the process. Okay, so let's look at a problem we did previously, okay, or we tried to do. This was the second problem we tried with the direct comparison test. we looked at the series of 1 over 2 plus the square root of n, and using the direct comparison test, we didn't draw any conclusion. The test was inconclusive, and so we still don't know whether that series converges or diverges. Well, if we use the limit comparison test, this is certainly a messy algebraic expression, okay? And so we'll make a decision here, is we're going to compare it with a appropriately chosen p-series. And so what we're going to do is we're going to create a p-series where we look at the highest power. Now, we can't have nothing in the numerator, and since there's no n's, the only thing we're going to have in the numerator is a 1. Okay. And then we look at the denominator, and we disregard anything that doesn't have an n in it, okay, any term. And there's only one term that has n in it, and it's the square root of n, and that's really n to the 1/2 power, isn't it? And so this is the series we're going to compare to, which is a p-series where p is the exponent 1/2, and 1/2 is less than or equal to 1, I really should say. And so we know in that case that this series diverges. So if we look at the limit, remember what the test is. The test is to look at the limit of the a sub n's over b sub n's. Here's the a sub n's, here's the b sub n's. Okay, and if that limit is positive and non-infinite, then they will either both converge or both diverge, and we already know one diverges. So they'd have to both diverge. Well, the a sub n's, of course, are the terms that we have here, 1 over 2 plus the square root of n. The b sub n's are the terms we have here, 1 over the square root of n. And then algebraically, we used to say invert and multiply. If we're dividing by a fraction, we multiply what we're dividing into, the numerator, by the reciprocal of the denominator. And when we do that, of course, we get a fraction that's the square root of n over 2 plus the square root of n. And as we did a moment ago, we would deal with this by multiplying the numerator and denominator both by 1 over the square root of n. That would give me a numerator that was a 1, and my denominator, I'd have 2 over the square root of n plus the square root of n over square root of n, which is just 1. Now, and when I look at this, of course, as n goes to infinity, this fraction is going to 0, so I have 1 over 0 plus 1, or just 1. Whoops. Now, the significance is that we have a limit here of those terms that is equal to 1, that ratio that's equal to 1. That limit is finite and positive. It's not 0, it's finite and positive. And so we conclude from the limit comparison test that both must converge or both must diverge. And since we already know one diverges, okay, what we were comparing to, then our original series must also diverge. And so now we know certainly, for certain, that the series that we could not determine the convergence or divergence previously with the direct comparison test, the limit comparison test lets us determine that it does in fact diverge. Well, I've got, I think, a couple of more problems here. I'm going to run through these rather quickly. There's several problems here. Example 3. And so I'm just showing you what we would do. We've got here, we want to know the convergence or divergence of this series. So what am I going to compare to? Well, here's what we do. No n terms at all in the numerator, okay? And so the numerator is just going to be 1. Now, what about the denominator? Well, here's where the highest power of n is. It's n cubed, and what the guideline is to disregard everything except the highest power of n, or k maybe, it could be, of course. So that means we disregard the 7, and we disregard the rest of this. And so we're going to compare to a series that's 1 over n cubed, which is a p-series. That's the point. And in that p-series, p is greater than 1, and so we know that p-series converges. So now we look at the limit of the a sub n's over the b sub n's. Here's the a sub n the terms. Here's the b sub n terms. So we look at that limit as n goes to infinity, and I've been a little lax here, haven't I? And so I will invert and multiply again. That gives me an n cubed in the numerator, and the denominator is 7n cubed minus 5n squared plus 1. Now I'm going to multiply the numerator and denominator by 1 over n cubed, so I get 1 in this position. And 7n cubed over n cubed is 7. And 5n squared over n cubed is 5 over n. And of course, 1 over n cubed, I can't simplify it all. And so when I look at the limit as n goes to infinity, I have 1 over 7 minus 0 plus 0, which is just 1/7. What's important? It's positive and it's finite. So that tells us both series either converge or both diverge, and we already know that one of them converges, so they both converge. Our series then converges. That's pretty easy to do, isn't it? Here's our example 4. Okay, so I'm looking at this series. I want to know about convergence or divergence. I need to come up with a p-series to compare to. And so what I do is I disregard all but the highest power of n in the numerator. Well, there's only one power of n. It's actually n to the 1/2 when we look at the square root of n. So I'm going to have a series that has square root of n in the numerator. I look at the denominator. I disregard the 2 coefficient. I disregard the plus 1. Highest power of n in the denominator is n squared. Now, this actually will simplify since this is n to the 1/2 power. Whoa. Yeah, since this is n to the 1/2 power, we'd actually be able to simplify that to 1 over n to the power 3/2. And again, that's a piece series. That's what we're doing each time in this case. And if that's a piece series, the p-value is bigger than 1, so this piece series converges. So now we look at the limit of the ratio. And in this case, I didn't go through it in this case. I'll let you deal with that. We're going to take this term, that's the a sub n's, and divide by the terms here. And when we do that, we'll end up with a limit of n squared over 2n squared plus 1. And we find out that that limit is actually 1/2. You can go through that, but that's the idea. So the limit would be 1/2. And that tells us then, of course, and that limit is finite and positive, so both converge or both diverge. We already know one of them converges, so they both converge. This converges. And the last one I want to look at here, this is really messy. Okay, the sum of n over the cube root of 8n to the 5th plus 7. So I'm creating a piece series, and here's the way I create it. I look at, disregard all but the highest power of n in the numerator. That's just n to the 1st power. I disregard all but the highest power of n in the denominator, but that cube root has something to do with the highest power of n. So I disregard the plus 7 and the coefficient 8. So I have cube root of n to the 5th, which is really n to the power 5/3. And when I take n over n to the power 5/3, it simplifies to 1 over n to the power 2/3. So my p series is the sum of 1 over n to the power 2/3, and p being 2/3, which is less than or equal to 1, I know this series diverges. So now I'm looking at the limit of the ratio. Now, if this limit of the terms, so here are the a sub n's, here are the b sub n's. If this limit is 0 or negative or infinity, then I can draw no conclusion. But when we go through the process here, and I'll leave that to you, we find out the limit is actually 1/2. Okay. And like I said, I'm just going to leave that to you. Now, the limit is 1/2, which is finite and positive, and so the the limit comparison test applies. And that's the issue. It applies. Well, if it applies, then both series converge or both diverge. We know one diverges, so the other diverges. So this series actually diverges by the use of the limit comparison test. Well, we've covered a lot of ground in a pretty short period of time, relatively speaking. And you're going to, I hope, enjoy doing problems determining the convergence or divergence of series based on these two tests. Good luck to you.